All right. My name is Paul Brewster from NASA Langley Research Center. This morning I had two people tell me that I was the last thing between them and dinner tonight. So I'm feeling the pressure today. I'm a little worried about this one now. So if I talk fast or anything, now you know why. It's just in a rush to get to dinner. So I'm going to talk about landing on the moon. Turns out landing on the moon is really hard. I think if you pay attention to the news, you might realize that it's actually hard to land on the moon. There are two real issues, two concerns you have about landing on the moon. One is how to do it safely, and one is how to do it precisely. Safely, you don't want to land on a slope, you don't want to land on a rock, you don't want to land on a crater. Precisely means you want to actually land where you intended to land. That's actually a really hard thing to do too. Apollo 14 barely got it right. Apollo made it look easy because they were successful, but it is a really hard thing to do. And we're going to where we're going now, lots of South Pole, really hard place to go, really rocky, and also lighting is a real problem on the South Pole. Hello?
Can we get a mic check online? Can you all hear us?
I hear you.
Oh, you can?
Yeah.
Oh, okay. Sorry about that.
Okay. So one of the bigger concerns, of course, is the lighting is really bad on the south, the farther south you go. So what you need is an instrument that can handle all of these concerns. Here's a typical landing ConOps. This is not specific to any particular mission. This is just here's what it would look like to land on the moon and how you would try to do that precisely and safely. You would start out about 50 kilometers away using an altimeter to figure out how high up you are. All you're really doing up here is just saying, here's how high up I am. Once you get a little bit closer, down to about 20 kilometers and down to 10 kilometers, you start actually looking at the terrain, looking for features and saying, do I recognize that? Do I recognize that? Once you find the feature you recognize, you say, I recognize that. Now I know where I am. That's called terrain relative navigation. We've been doing that for decades in missiles. Then when you get down to about a kilometer, you can then start looking at the ground and saying, now I'm close enough. I want to find the safe spot. I want to find the hazards. I want to avoid the hazards. I want to go to that safe spot. And then after you get down to about 500 meters, you start saying, okay, I found my safe spot. Now let's make sure I go to that safe spot. So there's sort of a trend there. And it would be really nice if we had an instrument that could do all of that. So that is where a flash LiDAR comes in. A flash LiDAR is obviously it's a LiDAR, a laser-based rangefinder. The difference between a flash LiDAR and other ones is that when it shoots out a laser pulse, the transmitter laser, it goes through a lens which diffuses it and spreads it out over the whole area. So it's illuminating the whole field of view that you want to look at. Say 100 meter by 100 meter field. It illuminates the whole area. And then you have a receiver optics that receives that back. And instead of having one detector there to measure the time of flight, you have a whole array of detectors there. Say 16,000 detectors. And so each one of those detectors measures the return of flight at the exact same time, off the exact same pulse. So you have no concerns about trying to figure out taking images or taking range measurements and then trying to figure out how the movement works out. The movement works great. This is better than a camera, a visual camera, because we take our own light. We don't have to worry about shadows. We don't have to worry about the sun. We don't have to worry about all the other hard things that a visual camera has. It works better than a scanning LiDAR because a scanning LiDAR is sitting there trying to move back and forth a whole bunch. And then you have to calculate that into your range. You have to have a good gimbal on it. You have to calculate all that. It's really hard with a scanning LiDAR. This removes all of those problems. It works really well. It has a couple disadvantages. The flash LiDAR does not have the resolution that you would have liked in a scanning LiDAR or a visual camera. But we have software. We can have software to overcome that problem. The software is very processing intensive. So I'm going to talk about that a little bit more. As a multifunctional flash LiDAR, here's how it would work. we started off with a flash LiDAR on the plans of doing the hazard detection, the hazard relative navigation. That's where we were planning on doing all this to begin with. And that's where you can illuminate the ground about 1 kilometer away. You can figure out, make a digital elevation map. From that map, you figure out your safe spots, you figure out where to go, and then you navigate down to that. And that's where that's been our plan the whole time. Then we realized that we can modify this. We can, by changing the optics out, rather than diffusing it over a big area, we can make a pencil tight beam. And we can shoot this, instead of going 1 kilometer, we can take this from 50 kilometers away. And we can turn the same flash LiDAR into an altimeter. And then we could also, as we get a little bit closer, we could expand the beam out a little bit. And so it's still not as wide as the bottom, the hazard detection one, but it's a tighter beam. And that will give us enough data to do the TRN. And we can run that out to about 20 kilometers. So we can use one instrument to do all of this, and life would be good. So here's what we have. To give you an example, on the right on the left there is a visual image of a building. That building is about 500 meters away. On the right is what the flash LiDAR would give you. It's been color mapped to show distance. So red means closer, green means farther away, yellow's in between. That's kind of what you have coming in. So what we need the software to do, we got all the normal software stuff, command and control the LiDAR camera, control the laser, control the optics, produce the telemetry, produce all these data sets we need, the range images, the altitude, the DEMS, the hazard maps, the safe sites, produce all those at the right speeds. But then the key thing, though, is there's a lot of data processing that has to go on to get that. That's not something we can just get. We have to do a lot of data processing. We have to generate those DEMS. We have to generate the hazard maps. We have to find the safe locations. So here's what the software might look like. Well, here's what it does. Here's a software flow. You notice it's kind of multimodal here, so whichever mode you're in. But it's also, if you notice, it's kind of a line. The range image goes in one end, and your data that you're looking for comes out the other end. Except for then you have that little mode change between whatever mode of the mission you're in. That's what the trickiest one of here is the create DEM one right there. That's used a couple times. That's the hardest part of this algorithm. So here's a detail of what the create DEM algorithm does. We often call this super resolution if you want to look up in the literature. It takes an image, takes 20 images, kind of over on the right, it takes 20 images and stitches them together over time to make a really high resolution DEM. The first image only creates a rough DEM, but as you add more and more in, they make a finer and finer version of the DEM. We're not scanning back and forth. Each one is illuminating the whole area, but if you add them up together, you get a really nice looking DEM. And that works really well. We've done a lot of experiments, but it works very well. There's just one problem with this algorithm. Current space flight processors do not have the power to do this. All the ones that we've seen out there that we could go buy right now that you can see on the shelf, they don't have the power. So I had to go looking a little bit to find a platform that could do all of this. And what I found was the GPU. This is the Jetson, you probably already know, it's the Jetson TX2i. There are several that have already flown in space. There's 3 specific missions I know of that have used the TX2i in space. I know several others who are planning on flying one in space as well, in development process. And there are actually several companies, I could even name you the companies, that actually will sell you a TX2i-based space grade flight processor. Or they'll call it space grade, for whatever that's worth. But that's what they built it as, that's what they'll advertise it as a space version of the TX2i. So I based it off of that. Could I implement that on an NVIDIA, on the TX2i? Many of those are going to be replaced by the Orin in the future, but right now that's what I'm basing off of. Because that's a picture of the one sitting on my desk. Because I can buy this. I've had this for years. So that says, what software do I want to run on it? Well, the TX2i runs off of Ubuntu. It's actually Jetson Linux. And then the NVIDIA provides all the drivers and everything for it. Then you use CUDA on top of that. And I'm doing an FFT, so I use their FFT application. And then there's a custom framework for GPU applications. That's something that I wrote. My previous project, I did CFS. There's other people in my branch doing F prime. And I kind of looked and realized I needed something specific to GPU programming. This kind of programming didn't really fit into those models because I had to worry about mostly it's the GPU memory buffers. I have to just pass around these memory buffers a lot, these pointers a lot, and they really didn't fit into those. So I made my own sort of framework to handle that. And then on top of that, I have all the modules, the telemetry command scheduling, stuff like that, but also the Lidar interface, the range filters, all the other modules on top of that. So a little bit about that GPU framework. I based it off of C++17. I don't know if that was the right idea or not. I actually wanted to learn C++17. So I kind of tried to do as much of the fancy stuff as I could. But it's a modular pipeline. I noticed when I showed you that software flow before, everything was sort of just a long line. So I made it a pipeline. So all it is you have, and it turns out a lot of CUDA code is just a pipeline. You just kind of have a module that passes to the next module, to the next module, to the next module. And then you just need to have a good buffering system in between the modules. So we do a triple buffered system between each module. It's triple buffered in case they don't run at the same rates. It can handle slowdowns. It can handle asynchronous data. And then because each one is running on its own thread. And each one has its own commands and its own telemetry. And that kind of, so that was the basic idea of how this all came together. Then we've actually done this in quite a bit of testing. Started off with some simulated tests of this algorithm. Now, if you take this image on the left, this is a simulated image. You can see on the scale that it's about 500 meters away. If you look closely on there, you can see like up in the yellow reds, there's little dots there, maybe you can kind of see. But if you look on the right, that's been converted into a DEM. Now that's after from just one image, you get one DEM. And you can see that on the left, it's a 128 by 128 image. On the right, it's a 1024 by 1024 image. It looks really chunky and blocky because we're not actually doing anything. We're just kind of orthorectifying it. But if I take 20 of them together, this was after one of them, but after I stitched 20 of them together, you see how it starts to fill itself out. And this is real data. I'm not interpolating anything. This is, by stitching the 20 DEMs together, I get a much, much better image than what we had. So that was how this all works together. We then went and took this, and we've done lots of flight tests with this, field tests. We started with a static test just out on the range. Then we went, and there at Langley, we have a gantry that goes about 60 meters up. We just hang it up there. You can kind of see there's a yellow up at the top with a basket hanging down. That's our instrument just kind of hanging up there looking down at the ground. And then we can do a drone test when that's a drone with our instrument hanging off of it. And we even did a helicopter test out in West Texas. And got some really good data that way. And just to kind of show you, this is from the real data. Here's what a final DEM may look like. This actually came out of the real-time GPU code. And for the future work, I wanted to talk about this a little bit. We still need to continue to refine it a little bit, but what we really have it ready to go for an ETU. I think we can actually fly this thing pretty soon. But we are looking at changing from the GPU. It turns out when we had in mind the GPU would work really well. I could convince somebody to let us fly a GPU on a landing. They're only going to be on for how many minutes is it land? Is descent landing? It's only going to be on for a few minutes. Maybe we can give it a risk. Then we started getting requirements back, hearing that people wanted it to last on the moon for 5 years. And I'm like, I don't think I can do a GPU for 5 years. I don't think I can pull that one off. So we're looking for hardware that actually can last 5 years. So the three options we're really looking at is the HPSC. We're just doing a straight FPGA approach. I'm not really interested in the FPGA, but management is. And also the AMD or the Xilinx Versal, which kind of is a hybrid of has a CPU and FPGA, and they have their AI engines on it as well. Looking at those as possible ones to replace it with. But that's my comments. All right, thanks.
Thank you.
Okay. Darn it, I have two questions, but I'll make it one, not only one. When you said GPU computing, what's the characteristics of the actual algorithm? Because GPUs are notorious for not being highly utilized, right? So if you're not highly utilized, you're going to burn your power and you're not going to get the perf. So is it straight arrays?
So the actual algorithm is a lot of image processing. It's a lot of handling. It's just a lot of for loops, which is what GPUs are good at. So this is why it's designed. It's why it actually does fit a GPU really well, because look at the MATLAB code. It's just a bunch of for loops, just going through pixel by pixel through an image. Now, what's kind of blowing it up on the FPGA was you had a lot of access to global memory, which kind of killed the FPGA implementation. And that's kind of hard on a GPU too, but I think it handles a little bit better.
All right, we'll take one online. Does the software use any open source for image processing, like OpenCV?
No, it does not. I thought about OpenCV. I think there's even been a push. Somebody that did like a flight version of OpenCV that kind of handles, kind of a flight version of it. OpenCV also isn't necessarily GPU based. It's a lot of it is CPU based, because I think Intel is actually behind a lot of it. So no, I have not. I've looked into OpenCV, but it's not it's kind of our own algorithm. So no, it doesn't need OpenCV.
Thank you. Can I take another question?
So, with all the recent landers landing on the moon, I think one thing we all saw was a lot of dust coming off the moon's surface.
Mm-hmm.
So I was wondering whether that, I guess, DEM stacking approach would be enough to kind of resolve the noise you get from all the dust coming off, or does it even interfere at all because it's a LiDAR-based system?
So I got great answers for that, because the guys who did scalps are in the booth, are in the cubicle next to me, and they just took a whole bunch of pictures of some plumes. If we're doing the hazard detection at a kilometer up, you're too far away. There's no ground effects there. That happens when you're getting much, much closer. And by that point, you probably do turn it off and just blind navigate. But by that point, you're 20, 30 meters off. So that effect actually doesn't really come into it, because we do it much farther away than before it really starts to become a problem.
Hello, thank you for the presentation. The word you mentioned about pipeline in the GPU, did it rely on CUDA streams for the kind of streaming, or it was just same purely CUDA coding?
So yeah, CUDA streams is, so each one of those modules was its own P thread, but then you can also do a CUDA stream, where each module could also have its own stream, and even have its own two streams, one for the calculation and one for the memory writes to the next module. Yeah, that's how that's being written. Yes.
All right, there's one more online. Did you build the LiDAR by yourself?
Did I? What was the question?
Did you build the LiDAR by yourself?
The LiDAR, no. The software, yes. The software, I didn't do the algorithm. The DEM algorithm is not mine, but everything else I did all the software, yes. But the LiDAR is, no, I'm not a hardware guy. I'm not a laser guy. There's a group there at Langley doing that. The same people who did the NDL, the navigation Doppler LiDAR. It's really the same people who are doing
I think
this.
the question mostly is it COTS or built in-house?
The camera itself is COTS. The system is built in-house. Combining it all together is built in-house, and then the processing is, of course, done in-house. This is designed to be the sister instrument that goes along with NDL, that's flew really well and it's done a great job measuring velocity as you land on the moon. It's kind of a sister instrument to that.
Thank you. We can take one more.
Thanks. We had the nice presentation about the HPSC earlier this today. Do you think this could also provide you the computational power you need for your system?
Yeah, my last slide was say I want to
okay.
do this on the HPSC.
Sorry. Then
I just
missed this slide.
gone, yeah, right there.
Okay. Yeah. No, I see. Okay, now I see. So,
I want
sorry.
to, now the GPU I've had on my desk for years, I actually have a Verso on my desk now. The HPSC I should have, we're expecting one. I think we're one of the early, we should get an early release of it whenever it's ready. And I hope to use the HPSC to figure out which one really works well. Or just straight CPU code. I mean, I could do it OpenCL maybe, but I'm not exactly a OpenCL fan.
Okay, thank you, Paul.